We see when we put an electric field across a nanomaterial, I'll talk about it in a bit, we arrange them to look like resistors. We call them nanors. We see heat all the time from dissipation of the electric field intensity. Sometimes we see excess heat. I'm going to show you where and how we quench it and make it go away. And too often we get a very high electric current avalanche. And that's caused a lot of loss of equipment over the last few years. And it led me to try and do an experiment where we could show excess heat on one side of the avalanche and watch it disappear on the other. And that will be the end of the talk. And the reason we do this is when we drive these nanomaterials, we have very high energy density and power density. That's the amount of excess energy out divided by the volume. And we find that the cold fusion materials are very far away from ordinary energy production systems. So what I'm going to try to talk about here in order, I'll review what we have seen in cold fusion in aqueous nickel systems using ordinary water and doping the ordinary water with increasing amounts of heavy water. And I'll introduce you to the nanomaterials and I'll show you some nanors. We'll talk about how we measure the electrical conduction, how we measure the excess energy when we see it. And then we'll be ready to talk about the avalanche. I'll show you that there are three regions in an avalanche. There's as you increase your electric field intensity across your nanomaterial, you get increasing current, and that's region 1, we call it. And you get a sudden avalanche, a massive amount of current through. To give you a rough idea, some of these materials change from impedances of terohms down to kiloohms. So if you have a ammeter, it's going to be made short shrift of. So we'll talk about that. And region 3 is on the other side of the avalanche, and there's no excess heat there, and I'll show you that. So let me give you some background of what we've seen over the last 25 years using nickel in ordinary water as a cold fusion system. So for example here, what we're looking at here is time, 0 to 35 hours, power output, and we're looking at two different systems. So what I try to do is always compare whatever I'm measuring to an ohmic control. I'll either take a wire wound resistor or a carbon composition resistor, and that way I'm able to measure to a normal 100% or just a little less than 100% efficiency. So for example here, we're putting in this amount of power here to the ohmic control in blue, and we're getting out this, the same amount we put in. This is a log plot, and we had to do that because here, when we put it into the nickel cathode, we get more out than we put in. Now, if we integrate over time and measure energy, which we see here in thousands of joules, this is excess energy. So we're measuring total energy here. So we're putting in this much energy, and what we see is this out. So this is our excess. So here's our excess power gain, which is right off this side. And here's our excess energy, which is right off this side. All of our curves, there are two sets of curves. Half of them are going to look like this over and over. So if you can get the pattern recognition in your mind, it'll be real easy. We measure the noise level. The reason we do that is if you drive a cold fusion system below the noise level, you're going to get an output from the noise level. It'll be an artificial false positive. You've got to measure noise. And that's one of the many controls we do. Now, this last one this was a nickel fusor. That's a wire-wound nickel cathode. And we put that in ultra-pure heavy water. I add no electrolytes. There's no salt, there's no potassium. We don't add lithium. In fact, what I try to do is I buy the most expensive grade of heavy water, which has the paramagnetic ions removed. So the cost goes from about $300 a liter to $3,000 a liter. And that gives us the best results. My feeling is the reason we fail in cold fusion is we set up alternate pathways that dissipate the energy. So to me, when people say cold fusion is fusion by electrolysis, I sort of laugh because in our experience, it's 1 minus electrolysis. If we get electrolysis, we lose. We're losing the phonons, we're losing the heat, we're changing the reaction. Anyway, here what we have is nickel is the cathode. It's in an ordinary water solution. and gold is the anode. We like gold a lot. I actually happen to prefer gold over platinum, and sometime we'll talk about that. And here you see after the measurement, the output falls back into the noise level. Now here we see a nickel system with ordinary water with platinum as the anode. And here too, we measure the noise. We look at the input to the ohma control. Here's our output, so we're getting less. There's no excess energy here. We've calibrated our system, 2 more ohma controls here. And here's the nickel cathode. We put in this, we get that out. We put in this, we get that out. We're getting energy gains of about 2 to 4 on a nickel ordinary water system. We reported this in fusion technology back when they were taking particles in cold fusion, thanks to George Miley. And here what we see is the energy integrated, which we read off the right in thousands of joules. So here's our input energy, here's our output energy. And one thing you might want to look at in addition to the noise level and seeing, in fact, the controls, the output's less, and here is more with the cold fusion device, is look at the slopes. When we have, and you'll see it better in some other ones, when we have an ohma control, these two are linear and usually overlapping. And when we see excess energy, they separate. So look for that over and over. See here, you see the excess energy, so they separate. And here, if you look closer, they're parallel over the ohma control. One other thing we do, if I get to this tomorrow, we have an equation that we developed for cold fusion, which I find very effective. It tells how to get cold fusion. It tells what quenches it. And in fact, it gives rise to my derivation of co-deposition and some other things, like these optimal operating points. When we look at the excess power, we find that these optimal operating points, this was one of the first ones we saw back in, I think this is 92 or 93, we found that we had to be very specific where we control the system. And it turns out this has been the same for palladium systems and nickel. You'll see this over and over, where we're very careful where we control it. Because if we don't control it, we're going to lose the over unity. Okay, so the way to make a lot of power is to make a lot of these little devices and gang them together. So let's talk a little more. We took these devices, and although it's not part of this talk, we've used various applications where we've connected them to Stirling engines. We showed this at the MIT course. And so, for example, this Stirling engine is driven by an ohmic resistor in here. This Stirling engine is driven by a cold fusion device here. And what we saw over and over was that for less power going into the cold fusion system, we got more energy out. This thing would be spinning around, and even with more power going to the ohmic control, you have to start the Stirling engines. They don't start by themselves. It wouldn't turn. So here was our data over several years. We started with Stirling engines in 2003. We ran them up to 2007. And we saw excess energy for both nickel with ordinary water and palladium with heavy water. The other thing we saw was that this optimal point operation also applies to devices that you drive with cold fusion. So if we look at our input power to the Stirling engine, here's 0 to 25 watts, and we look at our power gain, if we want to get the maximum amount of power, we drive here at 6 watts. Because, again, we see that if we push too hard for any one system, we're going to turn on other competitive processes that shut off what we really want. Here are some of the outputs. I'll just show you a few. We've got so many. Again, I apologize. In order to prepare for this, I didn't get to pull my slides, so I got too many. But you'll see it's basically over and over. What we try to do is we do parallel verification. We'll look at delta T, we'll look at heat flow, we'll do full bore calorimetry, we'll do serial verification, where we look at the core for these 3 parameters to measure if there's excess energy. And then we'll put it through a thermoelectric. We'll make electricity from the 2 sides, comparing the cold fusion cell to the ohmic control. We'll put it to a Stirling engine, and we'll even do calorimetry in the Stirling engine. So we end up having multiple parallel paths to show we have excess energy, and we'll do multiple serial paths as well. So here, for example, is one of the parallel paths where we're looking at the palladium fusor versus the ohmic control. And we see that the delta T that we get is much higher for the same amount of input. Now, one of the things we do, if you came to our open demonstration, we've done 2 open demos at MIT. We did the NANOR in 2012 in Peter's lab for 5 months. And we also did a FUSOR in 2003 for 5 days at ICCF-10. And what we do there is, we'll set up a cold fusion cell, and we'll put it in electrical series with an identical cell with a resistor in it. So we have 1 electrical current going through 2. We'll measure the voltage at both sites. This is DC, by the way, so it's easy to measure the input power. And what we showed at that demo was for the same electrical current going through, for a lower voltage, we had a higher temperature over the cold fusion side. And we showed that for 5 days. And so here, for example, you're looking at the output of that, where what we're seeing off on the left, again, is power. Off on the right is the integral, the amount of energy in joules. So here, for example, the input and the output to the ohmic control totally overlap. And here's the input in green, here's the output in this to the ohmic control. Here's the input to the FUSOR, here's the output. We're getting a gain of about 150% or so. So this is our excess energy. And there's a little heat after death here too, because when we turn off the power, we're still getting a little bit of heat coming out that's beyond the normal cooling of the material. By having paired calorimeters and paired materials, we're able to put up the heat after death as well, quantitatively. Okay, here's another way. Here's where we take a number of these FUSORs and then can measure serially and in parallel. So we'll look at the input power. We'll look at the calorimetry. Anyway, I'll just show you one more. This is interesting. When we take the energy from the core and put it to the Stirling engine, we actually lose the excess heat in the center. This is not a measurement error. By transferring the energy, you can see here we actually lose the overunit. Once we start the engine turn on, all of the excess is going to the motor. So this is not a measurement error at the core. Now let me show you something else. This is important. Back at ICCF 5, we reported that adding small amounts of heavy water to ordinary water nickel experiments increased the energy gain. But it was metallurgically destructive to the nickel. So for example, you see a FUSO here. We would use this as the cathode. So here's our virgin nickel. And after a bit of time, it would change its electrical resistance, it would change its color, and worse, they become non-useful in cold fusion. They become a control because they're permanently inactive. So for example, let's look at some data here. Here's our new FUSOR. This is a nickel ordinary water system. And here's our ohmic control. We like ohmic controls. And if we overdrive the FUSOR, we can actually change the material. You can see the color change. And we never see excess energy again. So here, for example, this is before it's destroyed. Here's ordinary water giving us excess energy, ordinary water nickel system. We can increase the gain by increasing the amount of D2O. So here's 3.7%. And there's the ohmic control. And here, for example, is if we look at this optimal operating point, so here we're looking at input power from 0 to 2 watts. Here's our power gain up to 200% peak. But if we damage the material by adding 15% heavy water, we come down to 0. It becomes equivalent to a control. And that's really important if you ever do experiments by mixing these. Hydrogen can not only interfere with the deuterium loading, but it may actually change some of the metals as well. We've never seen that with palladium, but we've only seen it with nickel. So now with that background, with nickel and ordinary water, let's switch to dry, preloaded nanomaterials. Now we've carried this work over a lot of years with a number of material, a number of people. We've looked at electrical breakdown with Brian Ahern, and then we went on to ultrasonic irradiation, direct electricity production, and some imaging. I'll show you some of these things here. And recently at ICCF 18, we reported the results of the magnetic effects. Okay, first of all, there's a lot of nanomaterials available. I'm sorry, what? And if you can interrupt if there's any questions. Was there something? No, okay. Basically, the nanomaterials include co-deposition structures, which several of us make different ways. We could have a whole lecture on that because in fact there are different kinds of co-deposition. It may not be clear, but co-deposition on palladium is very different from co-deposition on silver or copper or nickel, and they act differently. The other thing that we use are Arata developed a number of both palladium black and zirconium oxide materials, and those are what I'll mainly show you today. But I'd like you to see how many kinds of nanomaterials there are. This is a completely wide open field. So let's talk about the ones that I'm going to show you today, which are these zirconium oxide nanomaterials. ZrO2, which acts as an insulator. I like to think of these things as a chocolate chip cookie. So the chips are actually a binary metal. They're palladium and deuterium, or a ternary metal, palladium and nickel and deuterium, or in some cases hydrogen. And what we do is we pay very keen attention to their size. It turns out that the size of the material, as you'll hear tomorrow from Brian Ahern, is key to their function. And we've spent a lot of time trying to examine how size plays a role. Basically, when we have the nanomaterials, we go to very high loadings. We see loadings of 3 easily, maybe more. And some of the ones I'll show you, I calculate 10. I don't think it's 10 or 3 in the classic sense. I think we have some very shallow traps where the deuterium is placed. These may not be active sites. And therefore, I think when we measure 3 or 7, we're actually looking at the total amount in the container and probably not in the active sites. So what's a nano? What we did is we built these materials. Nanomaterials are very dangerous if you inhale them. Palladium, not so much, because you can put it anywhere in the body, but nickel is a bad actor in the body. And as a doctor, we often see people with dermatitis from nickel, and so it's something you don't want to get in your body. So we've made a number of these nanors. These are our most recent, the Series 7. And what we do is we take these nanomaterials and we further process them to get more deuterium and more protium in them. And it's a many multi-month process. So when you see these, the nanomaterials may only take 2 or 3 weeks to make, but fully processed, it's up to 3 to 4 months. The total amount of energy making them is under 100 joules. So when our outputs are thousands of joules, we're way over the amount we're putting in to make them. But you need that number too. So what's a nanor? Let's go back to that. These are the nanors. The first ones we saw, we measured electrical avalanche. We were not getting excess energy. We finally got a tiny amount, I'll show you, of excess energy in Series 3. We learned how to hyperload them. The Series 6 were the ones we showed at MIT, at Peter's course. And then Series 7, we were trying to improve hyperloading. And we finally went above 1 watt power gain. And we're doing some other stuff with high temperature. We can talk about some other time. What we tend to do is we'll put a nanor next to a normal control, and we'll swaddle the whole thing with a high specific heat material, either paraffin or water or oil, some material. So this will all be filled, and we'll put multiple probes in. But the key is to get these two very close together. So when we measure the temperature to get the thermometry, these two are very close, and this is far away. And we measure both the temperature at multiple places on the inside, and we also measure outside the container. Okay. This slide came from the patent office. Has always treated me fairly badly. I've submitted a number of patents which aren't even on cold fusion, and they throw them up for cold fusion. The one that we might talk about tomorrow, I understand, I built a device to measure loading. And they threw it out because they said I claimed excess heat. The words excess heat were not even in the patent application. In fact, there was nothing in the patent application on cold fusion except for this device is applicable to cold fusion as well as measuring heat from palladium loaded with hydrogen. Anyway, after giving me grief for years, I filed a patent last June, 2 Junes ago, and 3 weeks later, they made it secret. So something in it was interesting, and that's where all this came from. So slowly, actually, we've been talking about this at the IAP course, and we'll open it up over time. Now, as I say, I find there are theories that really help me. The equation that I'll show tomorrow, on Sunday, that we use for loading has been my #1 prime equation for getting these things to work. The other thing that really helps was the discovery of Fran Tanzeller and Mike McCubry at SRI, where they measured resistive ratio to loading. And I just want to show you, we found the same thing for the nanomaterials. As we load the nanomaterials, increase loading, the resistive ratio goes up and comes down. So it turns out, when you find theories that work for aqueous, we're finding that they sometimes also work for the dry materials too. So let's talk about electrical conduction. It's actually rather easy. These are 2 terminal devices driven by DC. So the input electric power is V times I. I don't subtract any thermoneutral potential. And we can measure the voltage and currents with incredibly good accuracies. And the power gain is defined as that. Again, we don't use any corrections. And what we do is, I like actually to, as close as I can, match the impedance of my power supply to my device that I'm driving. Maybe some of you know that's what you should do. It's not often talked about in this field, but that's why you see all these power supplies. And so we drive one in one bay and we drive the other one the other bay. Sometimes we have 2 things running at the same time. And how do we measure excess energy? Well, we do the thermometry, but by comparing it to an ohmic control, we actually can do really good calorimetry. And here's how we do it. For verification, what we'll do, as I said, in parallel, we will measure delta T, we will measure the heat flow, and then we'll do full bore calorimetry. By measuring noise, power, and time integration, we rule out false positives. To measure the heat flow, we use Fourier's equation, and we put the things together like this. See, we'll have this one, in this cartoon, we'll have the nanor and the ohmic control here. We'll put 2 temperature devices on each side, multiple temperature devices here, and put the whole thing into a very large, high specific heat material. And so, and the other reason I showed this is we looked at magnetic fields as well. Magnets up here. Okay, so what we do is, in order to make sure we know what we're doing, we do thermal waveform reconstruction. A lot of people in the field don't do that. And what that means is, let's say you have a calorimeter. Is it any good? Well, one way to tell if it's good is to put a resistor in, put a square wave in the resistor, and see if you measure a square wave out. Seems sort of logical. A lot of people don't. And in fact, if you do, here's, for example, is a run that we did. Here's the ohmic control. Here was the cold fusion device that didn't give excess energy for this one. But you see, we're able to calibrate, even on the control, that we have good calorimetry. If you put a square wave in, you want to be able to get a square wave out, or you can't believe it. The other thing we do that we find really important is the control of these devices. It turns out if you have a material that changes its impedance from 10 terohms to 10 kiloohms, you need a way to control it so you don't blow out all of your devices. And so that's what this is all about. Let's talk about electrical avalanche. So the first ones we built, I thought this would be easy, and it wasn't, because there was no excess energy, and we measured a very high input impedance. I went back and did it again and again. And the first thing I discovered eventually was, wow, some of these materials have a sudden breakdown. And for this one, it was at 23 volts. Some of them are higher. Generally, they break down anywhere between 20 volts and 1,000 volts. Yes?
Mitchell, if you got an avalanche, could you stop it? Could you, such that if you were using one of these nanners in a control circuit, it wouldn't get a surge or something from the avalanche?
Hadn't even thought about it. I guess I was just thinking about how can I measure both sides without blowing out my equipment. So you're...
Well, all I'm saying is that if you got an avalanche, it's uncontrolled at that moment.
It's true. I had never thought of stopping it. We'll have to think of what that implies. Let me show you how it occurs if you don't stop it, since that's the only data I have right now. Here we see the breakdown. And what we see, we went back again and we looked at these breakdowns over and over. Well contained here, sudden breakdown, massive power dissipation goes up. And it turns out, for example, this one had an impedance here, 2 megohms down to 4 kiloohms. And the more recent nanomaterials, as I say, we actually go as high as 100 terohms for impedance. And it's just a massive thing. You know, you're doing the experiment, you're running it at 2,000 volts, your ammeter flashes, you check your pulse. You're allowed to crash. It's the first time it was very nerve-wracking. Then I got used to it, and then I decided I've got to just try and measure on both sides, and that'll be the last thing we come to at the end. So let's look at region 1. Finally, by series 3 nanors, we started getting excess heat. And here's the first one we saw. So here's our aroma control, and here's the first nanor that we started getting heat on. Now this was a nickel. This is zirconium oxide with nickel, to which I put protein. And a very tiny amount. I mean, it's just, but here we see these are parallel. Here we see a slight separation. Very, very primitive. One thing we discovered right away was that in region 3 we lose the excess energy. Here, for example, here's our aroma control. These match input, output. Here's our input to the, put it backwards here. Yeah, here's our, no. This is our input. We're getting less out than we get in. I think these are backwards. The fact is that we end up losing the energy in region 3. We took a break from that for a while and tried to increase the outputs by improving the loading. And those were the series 5 and 6 that we showed at MIT. So here was one that, this is just at the turn of the year. Here's our OMA control. This is a calibration pulse. We put a calibration pulse in at the beginning of every run because we put ammeters in on both of our sides, and we want to make sure everything's calibrated. So we check the voltage, we check the current on our systems, and then we do the run. So here's our input to the OMA control. Here is our delta T normalized to input power. So the reason we normalize the input power is if you don't, this keeps rising. But by dividing by how much you put in, it becomes a straight line, more or less. And so then we can take the ratio of this to this, and that's our energy gain. You got that? The easy way to do it is by, instead of delta T, we do delta T to input power, and then these ratios are our energy gain, which here's like 3 or 4. Input, output. Input, output. And the reason we have multiple inputs is we're looking for the optimal operating point. Okay? We want to characterize these devices so after we have our exploratory stage, we can go to our exploitation stage and drive them. Here's another one. I'll just run through these. Basically, this one is heat flow. Again, what we do is look at multiple ways. So let's see, this is run 1A, this is run 1A. So here what we're doing is we're looking at delta T. Here we're looking at the heat flow coming out. So it's 2 independent methods to make sure we get excess heat. And we're really happy when we see 3 independent methods. That's what we shoot for. So here, the heat flow, here's our ratio, like energy gain of 2 to 3. And here's our full board calorimetry. So here's our input, here's our output, a little lagging. Here's our input to the nanor, here's our output, here's a calibration pulse. Here's our input to the OMA control, here's the nanor again, nice output. And again, you can see that, well, maybe you can't see, these are overlapping, and here they separate. This is our energy gain right here. This is how the electrical resistance changes over time. That's a whole separate issue. This is another reason you need a controller. You see, our aroma controls are very well behaved, but the nanors never are. And then we built some other ones. I'll just run through them. The course began January 25th, so about now I'm getting ready to call Peter up, going, okay, we'll bring it in. Now the other thing that's interesting is we discovered something only recently going back. In the calibration pulses, usually what happens is, like, here's the OMA control, here's our calibration pulse, here's the output, here's one, here's the output, voltage and current. And what's interesting is the current is in phase with the voltage. And that's not always true. Some of our best performing nanors, and we don't know why, when we do the calibration pulses, the current lags the voltage. So this is something we just noted as everyone in the group began looking at the data at the course. And if anybody here has any idea,